This is Algebra Lesson 5-8, Graphing Absolute Value Functions. Remember, an absolute value function has a V-shaped graph that either opens upward or opens downward. We've talked about this in Chapter 4 when we graphed some absolute value functions. The parent function for the family of absolute value functions is y equals the absolute value of x. A translation is a shift of a graph horizontally, vertically, or both. It basically means you pick the entire graph up, keep it the same size and shape, and just move it someplace else. Okay, so you pick the graph up and you move it to the left 5, or you pick the graph up and you move it diagonally down the page. It's in a different position, but is exactly the same size and shape. There is such a thing in math called a piecewise function. That's a function that has different rules for different parts of its domain. For example, when x is greater than 0, the absolute value of x equals x. But when x is less than 0, the absolute value of x could equal negative x. And this seems a bit confusing for right now, but it will make a whole lot more sense when I go through an example a little bit later in the lesson. A step function is a function that pairs every number in an interval with a single value. Think of a step function as like stamps on a letter. If your letter weighs less than an ounce or less, you have to put one stamp on it. Your letter can weigh half an ounce. You still have to put that one forever stamp on it. If it weighs more than an ounce, even if it's 1.02 ounces, it's just barely over an ounce, you will step up to having to go to that second stamp. That's why it's called a step function. It literally just jumps up a whole bunch of values. All right, we are going to talk today about absolute value graphs first. So let's take a look at some things. Let's graph the same three equations on the same x and y axis. We're going to put them in different colors so they'll be easy to see. And I'll label them separately, and I'll label them in their different colors as well. So I'm going to put the parent function in red. So my parent function of y equals the absolute value of x is in red, and then y is equal to x plus 2. Let's put the absolute value of x plus 2. Let's put that in blue. And last but not least, let's put the y equals the absolute value of x minus 4. Let's put that in purple. Okay, so we probably should make a table of values for all of these. So I will make a really quick table of values for all of these. For the parent function, it's pretty simple. Okay? If it's the absolute value, so if I had negative 2, negative 1, 0, 1, and 2, if x is negative 2, the absolute value of negative 2 is 2, the absolute value of negative 1 is 1, the absolute value of 0 is 0, the absolute value of 1 is 1, and the absolute value of 2 is 2. So my parent function, which is going to be in red, will have the following, will look like this. And remember, it's a V-shaped graph. Use your ruler to make sure these end up to be looking very nice and tidy. So here is my V-shaped graph for my parent function. I'm a little off on this one, so I have to adjust it just a little bit. There we go. So there's my parent function. There's y equals the absolute value of x. Now, if I use y equals the absolute value of x plus 2, need a little bit more space for this one. I'm still going to use the same points, negative 2, negative 1, 0, 1, and 2. So we'll have the absolute value of negative 2, which is 2, plus 2, which is 4. The absolute value of negative 1, which is 1, plus 2, which is 3. The absolute value of 0 is 0, plus 2 is 2. The absolute value of 1 is equal to 1, plus 2 is 3. The absolute value of 2 is equal to 2, plus 2, which is 4. So we'll graph this one. Negative 2, positive 4, negative 1, positive 3, 0, 2, 1, 3, and 2, 4. So this absolute value function looks like this blue one here. Looks like that. All right. So this is equation number 2. Now let's look at equation number 3. Again, I'm going to draw an x and y table. Eventually, you're not going to need these. And I'll show you that today, and you'll be really thrilled to figure out how well this works. Now we're going to the absolute value of x minus 4. So I'm going to use the same points again, -2, -1, 0, 1, and 2. So I have the absolute value of -2 is 2. 2 minus 4 is -2. Absolute value of -1 is 1. 1 minus 2 is -1. Absolute value of 0 is 0. Minus 4 is -4. Absolute value of 1 is 1. Minus 4 is -3. Oh, I messed that up. This should be, over here it should be 4. This should be -3. Haha, it does help if you put down the right number you're supposed to be putting down. Proves I'm human again. Absolute value of the last one, absolute value of 2 is 2. 2 minus 4, I almost did it again, is -2. Okay, so if I go to -2, -2, -1, -3, 0, -4, 1, -3, and 2, -2, I have another V-shaped graph, which is what I'm supposed to have. Okay. Here is this one. Should look like, make sure I go, there we go. And here should look like that. So there's equation number 3. Oops, I don't want to write it in arrows. Okay, so how are each of these graphs the same? Well, we can all see that they all are the same V-shaped graph, aren't they? All right, they have the same shape. How are they different? Well, if you look at it, their vertex, or where they cross the y-axis, the y-intercept is different, isn't it? The parent function crosses the y-intercept at 0, 0. The blue function crosses at 0, 2. And the purple function crosses at 0, -4. Okay, so each of these graphs has a different y-intercept. Now, if we were to look carefully at each one of these graphs, let's go back to these graphs again, and let's look at the equation of them. If we look at the red graph, that's my parent function. If you pay attention to it, you'll notice that here's my vertex right here at 0, 0. To get to my next point, I go up 1, right 1, up 1, right 1, up 1, right 1. I'm just stepping up these steps this way, and I'm doing the same thing over here. So my parent function always looks like a V graph where you're going up 1, right 1, up 1, left 1, up 1, right 1, up, up 1, right 1, up 1, right 1, up 1, right 1 on the right side, up 1, left 1, up 1, left 1, up 1, left 1 on the left side. You'll notice the blue graph has a +2 right here. And what is the y-intercept? It is at 0, 2. The purple graph has a -4 after the absolute value symbol. What is its y-intercept? Its y-intercept is 0, -4. So you should notice then that if a graph is in the form of y equals the absolute value of x plus something, you're shifting your graph up that many units. And if your graph is y equals the absolute value of x minus something, then you're shifting your graph down that many units. This gives us a general form of an equation for an absolute value. A vertical translation. The graph of y equals the absolute value of x plus k is a translation of y equals the absolute value of x. If you let k be a positive number, then y equals the absolute value of x plus k translates the graph up k units, while y equals the absolute value of x minus k translates the graph down k units. Okay. Since the above is true for absolute value translations vertically, you can easily write the equation of an absolute value equation if you know how far you're going to translate it. For example, if I know my parent function is y equals absolute value of x, like it says, I'm going to translate it down 9 units, 9 units down. So that means I'm going to have y equals the absolute value of x minus 9. Because it's going down, it's going to be negative. If I'm going to go up 3.5 units, then I'm going to have y equals the absolute value of x plus 3.5. Vertical translations are very simple. They do exactly what your brain thinks they should do. If you go down, if you're going negative, you're going down. If you're going positive, you're going up. And that means that the only thing in the absolute value symbol is your x. The number comes outside of the absolute value, and that tells you that it's a vertical translation up or down. Okay, which means I can graph these fairly simply. I don't have to write my parent function, but I could if I wanted to. You can draw the parent function if you like to, or you can just look at this and say, okay, I'm going to graph y equals the absolute value of x minus 4. I know my parent function would be at the origin. I know this is going to translate that parent function 4 units down from the origin, so I'm going to start here at negative 4. Remember what I said about the parent function. To get the next points, you're going up 1, right 1, up 1, right 1, up 1, right 1. Go back to that point at 0, negative 4, and then go up 1, left 1, up 1, left 1, up 1, left 1. And now all we simply need to do is to draw our graph. So there's that. And there's that. And I did not draw that very well. I started getting off. This is where you need to make sure you're really careful with your ruler so you don't get your points off. Because I'm off here. There we go. This one is off a little as well. Oops, I didn't realize that was 2 different graphs. Let's get rid of that guy. So let's choose him, get rid of him. And let's just extend this one. No, I want to extend it. No. There we go. That's better. And of course, I should label my graph. Always label your graph. Always label your axes too. X, y, and this is y equals the absolute value of x minus 4. You don't label these as 1 and 2 because you only have one graph. So please label it with its actual label, y equals the absolute value of x minus 4. Number 2 here asks us to graph y equals the absolute value of x plus 5.5. So here I'm going to go to 5.5, which is about here. And then I'm going to go up 1, right 1, up 1, right 1, up 1, right 1. And then I'm going to go back to that 5.5 point, and I'm going to go up 1, left 1, up 1, left 1, up 1, left 1. And I'm going to draw my lovely little graphs. And they should be going through all the half points. Like so. And of course, you should label it y equals the absolute value of x plus 5.5. These are vertical translations, translations up and down from our parent function. We moved the parent function literally up and down. Now let's see what happens when we do something slightly different. Let's look at another set of absolute value equations. We're going to create tables of values and graph them on the same x and y axis. My parent function, I already know how to graph that, so I'm going to graph that in red. It starts at the origin, up 1, right 1, up 1, right 1, up 1, right 1, up 1, left 1, up 1, left 1, up 1, left 1. Graph this in red. There we go. There we go there. So there's my first equation. So this one is equation 1. I'm going to graph y equals absolute value of x plus 2. Now notice here the 2 is inside the absolute value symbol. So if I do absolute value of x plus 2, everything's in the absolute value. Let's use my famous negative 2, negative 1, 0, 1, and 2. So we'll have the absolute value of negative 2 plus 2. That's going to be 0. The absolute value of 0 is 0. Absolute value of negative 1 plus 2 is the absolute value of 1, which is 1. Absolute value of 0 plus 2 is going to be 2. The absolute value of 1 plus 2 is going to be 3. The absolute value of 2 plus 2 is going to be 4. Okay, so negative 2, 0, negative 1, 1, negative Oops, that was the wrong way. I got to graph the right way. Negative 1, 1 is here. 0, 2, 1, 3, 2, 4. This looks like it's a straight line, which means I obviously need to go into the negatives a bit more. So let's pull a few negatives, more negatives. Let's use negative 3 and negative 4 really quickly. So we'll have the absolute value of negative 3 plus 2, which is the absolute value of negative 1, which is 1. And the absolute value of negative 4 plus 2 is equal to absolute value of negative 2, which is 2. So I'll choose the point negative 3, 1, and negative 4, 2. And now I can draw my V-graph, because now I can see that it's a definite V-graph. I knew it had to be a V-graph because it's an absolute value graph. And all absolute value graphs are V's or upside down V's. So this one goes here. Okay, so here's equation number 2. All right, let's do the next one. Whoops, I wanted this one to be in purple. Equation number 3 is going to be in purple. I'm doing the absolute value of x minus 2. I'm going to use more negatives and more positives this time because I already knew what happened with the last time when I didn't use enough points. So I'm going to choose negative 2, negative 1, 0, 1, 2, 3, and 4. So I have the absolute value of negative 2 minus 2, which is the absolute value of negative 4, which is 4. Absolute value of negative 1 minus 2, which is the absolute value of negative 3, which is 3. The absolute value of 0 minus 2, which is the absolute value of negative 2, which is 2. Absolute value of 1 minus 2 is equal to absolute value of negative 1, which is 1. I haven't turned yet. The absolute value of 2 minus 2 is the absolute value of 0, which is just 0. The absolute value of 3 minus 2 is the absolute value of 1, which is 1. The absolute value of 4 minus 2, which is the absolute value of 2, which is 2. So negative 2, positive 4, 1, 2, 3, 4, that's here. Negative 1, positive 3, 0, 2, 1, 1. Oops, that's right there. 2, 0. So far I've got a straight line. 3, 1. I finally get to my V shape to it. 4, 2. All right, so now when I draw my graph, my V shape is going this way. So there's graph number 3. Oh, I never labeled graph number 1. Bad me. There you go. So if we look at this, okay, we've used different colors. We've seen how are these graphs the same? Still the same V shape, aren't they? Still the same V-shaped graph, just like they were a V-shaped graph before. Okay, we had that lovely little V-shaped graph before, so we have that here. So we have our nice little V shape. But if you notice, they're not shifting up and down, they're shifting left and right. So the graphs have the same shape. Graphs are the same shape. However, this time, they're shifting to the right and to the left. Okay. They're shifted right or left. And we're going to look at how they are shifted. Okay. Let's take a look at the blue graph. The blue graph had an equation of y equals the absolute value of x plus 2, but it was shifted to the right. Excuse me, to the left 2 units. This was shifted left 2 units. The purple graph had the graph of y equals the absolute value of x minus 2, and it was shifted right 2 units. So if you look at it, it's exactly backwards of what your brain would think. Your brain would think +2 should go to the right and -2 should go to the left. But when you apply the absolute value, it actually shifts it the other direction. So if you have something that's in the absolute value symbol and it's added to the x, you're going to shift it to the left. And if you have something that's inside the absolute value symbol and it's subtracted from the x, you're going to shift it right. This leads to the horizontal translations of an absolute value graph. For positive number h, y equals the absolute value of x plus h translates the graph of y equals the absolute value of x by h units to the left. And for a positive number h, y equals the absolute value of x minus h translates the graph of y equals the absolute value of x by h units to the right. So I always tell the students it's probably a good idea to pay attention to your graphs. And again, you're just taking that parent function and you're moving it right or left or up and down. And sometimes you can do both. So if we have y equals the absolute value of x minus 4, this is actually going to the right 4 units. And I tell people just do this at the top of their paper so that they know, oh, that one's going to the right 4 units. So here's x, here's y. Normally my vertex is here. If I'm going right 4 units, 1, 2, 3, 4, my vertex is going to be here. Up 1, right 1, up 1, right 1, up 1, right 1. Go back to the 4, 0. Up 1, left 1, up 1, left 1, up 1, left 1. And I can draw my line using my handy dandy little straight edge. And I'd label it y equals the absolute value of x minus 4. And it's really hard to say these out loud because the absolute value of x minus 4 is different than the absolute value of x minus 4. Notice I make a dramatic pause when the absolute value is only around the variable. Number 2 here, this one's going to go left 1.5 units. So instead of being at 0, 0, I'm going to go to left 1.5 units. So then I'm going to go up 1, right 1. Be careful because you have to be in the middle of things. Up 1, right 1, up 1, right 1, up 1, left 1, up 1, left 1, up 1, left 1. And do that over here. And then make sure we label it y equals the absolute value of x plus 1.5. And of course, label your x and y axis. And again, just like before, we could write an equation if we knew it was a translation of the absolute value of x. So if I want to write an equation of the y equals the absolute value of x, and I'm translating it 10 units to the left, okay, I'm going left, which means it's going to be positive. So it's going to be y equals the absolute value of x plus 10, because it goes the opposite of what your brain thinks. Okay. If I'm going to go to the right 7 units, y equals the absolute value of x minus 7 is in the absolute value symbol here. Now, letter C here, we're going to do both. We're going to go 3 units right and 4 units down. So 3 units right means I'm going to go y equals the absolute value of x minus 3. And 4 units down is going to be minus 4. The vertical does exactly what you think it does. The horizontal does exactly the opposite of what you think it should. Okay, so right means I'm going to subtract, down means I'm going to subtract, right means I'm going to subtract, left means I'm going to add. The last thing we're going to talk about is we're going to talk about a piecewise function, otherwise known as a step function. Okay, they can be called basically the same thing. It's piecewise function, step function. Okay. A school will charter buses so that the student body can attend a football game. Each bus holds a maximum of 60 students. Make a graph that models the relationship between the number of students x that go to the game by bus and the number of buses y that are needed. So if x is the number of students, so let's put down number of students here. And y is number of buses. It's really hard for me to write sideways. why it's not quite as nice of handwriting. Okay, so the thing that we have to realize is if we have 0 students going to the game, that means we have 0 buses. We increase by 1 bus every time we hit over 60 students. Okay, so on the 61st student, we would need 2 buses. If we have 1 student, we would need 1 bus. If we had 59 students, we still need 1 bus. Once we get to 60 students, we still only need 1 bus, but as soon as we get to 61 students, now we need 2 buses. Does that make sense? Every 60 students, we need an additional bus. So if I decide that, obviously I don't need as many buses as I have students, because it's not a 1-to-1 ratio. So the number of buses I'm going to count by 1. So I'm going to have 0, 1, 2, 3, 4, 5, 6, 7. I don't know how many buses I'm going to take. Depends on how many people I want to go. Okay. If no students go, we don't need any buses. Yeah, we don't need anything. Okay. I'm going to count by 20s here. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, 260, 280, 300. That's probably good enough. You'll get the idea from this. Okay, now we're going to draw a closed circle when the end point is part of the graph. So if I have 0 students, I need 0 buses. I just need an open circle here. However, if I have 1 student, okay, if I have 0 students all the way up to 60 students, okay, so here I need 1 bus. If I have no students, I don't need a bus. But if I have 60 students, I need a bus. And it can hold 60 students, so that would be a closed circle at 60. It's an open circle at 0 because I don't need a bus if I have no students. Okay, and I have a line that goes between those. Now, let's say I have 65 students. Then I'm going to need a second bus. The 60th student goes on the first bus, so this is open. And I'm going to need that second bus all the way till I hit 120 students. That one's closed. And again, we're going to draw a line that goes and connects those. If I have 120 students, I only need 2 buses. If I have 121 students, all of a sudden I need a third bus. So 120 students, this is going to be open all the way till I get to 180 students, and this is going to be closed right here at 180. As soon as I hit that 181st student, I'm going to need another bus, so I have an open circle there, and all the way to 240, and I close it there because every 60 students, I need another bus. So at 240, I don't need another bus at 240, but I do at 241 all the way to 300. See how this is a step function? It steps up. It almost looks like steps. Okay, and this is what a step function looks like. I only need 1 bus if I have 1 student all the way to 60 students. But as soon as I hit that 61st student, I'm going to need a second bus. Whether I put 59 on one and 1 on the next one, that's different. But as soon as I hit that 61st student, I'm going to need a second bus. As soon as I hit that 121st student, I'm going to need a third bus. So it steps up to the next bus needed as soon as you hit a specific value. That's what a step function talks about. You're not going to use a lot of them in this class, but you would when you get into some other classes, like my financial algebra class uses step functions all the time. All right, our closure question for this lesson. What is the difference between a horizontal translation and a vertical translation? In other words, a horizontal translation moves the graph how? A vertical translation moves the graph how? Okay, that's what I want you to answer.